Okay, today we'll be taking this paper, which is so if you know almost, I believe that you can learn a lot in machine learning just by reading papers, and that's pretty much how any new thing in machine learning is also documented, right? You write papers. So this is a really cool paper called Perceiver: General Perception with Iterative Attention, and this is very recent, just like 2 months ago 2 months ago. That's how recent this paper is. This is a really new machine learning model, a machine learning technique. So what we'll be doing today is we'll be taking this paper. This is like 40 pages. I'll not make you read all of it. That's not humanly possible. So what I'll do is I have already read this paper and we'll try to read this paper together and I'll abstract out a lot of things for you. So there is some cool math over here which might be a bit heavy. So I'll abstract out everything for you. And that's how we'll be discussing this paper. So this paper is by Google DeepMind. And this is the paper we'll be talking about. This is super new. And this is also a state of the art technique, state of the art model. So if you don't know what state of the art models are, that's just another way to say best models in the world, one of the best models in the world. So this is one of the best models in the world. Something really cool about this. Okay, let's do this thing. Let's read the abstract together and then we'll see what's actually cool about this. You'll soon see, just we'll read the abstract together. I'll not read the whole thing. I'll abstract out a lot for you. And then you'll see why I really love, why I want to talk about this paper. But before we start doing so, uh, can you see my OneNote screen? Just let me know if you can see my OneNote screen because that's where we'll be doing kind of all the stuff. Thanks. Thanks for confirming that, Hassan. Um, cool. So the first thing, as I say, is we'll read out the title: Perceiver, a general perception with iterative attention. Just like all paper titles, this does not give away much. Let's see. So the first thing this shows me is this first motivates how the name Perceiver came. So this says biological systems perceive the world by simultaneously processing high dimensional inputs from modalities as diverse as vision, audio, touch, proprioception. Okay, cool. So, uh, and the perception models used in deep learning, on the other hand, are designed for individual modalities, often relying on domain-specific assumptions. Okay, so what do you understand from this? So I understand from this that this part of the abstract essentially tells me that, let's say I'm a human, which I am, and if I want to perceive the world around me, if I want to perceive the world around me, what I usually do is I simultaneously process high dimensional input. So what could this input be? This input could be touch, could be audio. And so what you are doing, what I am doing, what everyone is doing, all humans are doing, is they are taking all of this kind of data simultaneously and processing all of this simultaneously. A lot of these data, we are processing everything simultaneously in our brain, right? And then making sense of the world around us. Or as they say, we are then perceiving the world, which is also how perceiver came across. Okay, so but the problem with machine learning is in machine learning, we take each of these as a separate subjects. You probably build a model for audio. So let's say I'll just call this model. So this is one model represented by capital M. This is another model for vision and so on. So we have all of these different models, and every machine learning model is only working on one kind of modality of the data. If I have if there are some really state-of-the-art models like ResNet, VITs, all of them only work on vision. They don't want anything to do with audio data. They only work on vision data. So, but whereas we want machine learning systems to imitate humans, do human-like tasks, and humans take all of this data together, all of these kinds of data, what they refer to as modalities of data, individual modalities. So modalities is just all of these different kinds of data. Humans take all of them together. Machine learning algorithms do not. Do you see the flaw in there? Yeah, that's what this paper is kind of aiming to fix. Before reading more about more in the abstract, let's go down. This is one of the kind of cool things in the paper. They have a cool figure of how the model works. So if I just see this from what we have read until now, I can easily say that what this does is this interleaves self-attention with cross-attention mechanism. So, and this right here, which is what they call byte array, is just our image, or could be any kind of data, right? Because in this paper, what we want to do is we want to make one model which can take all these kinds of data, could be touch, audio, vision, and many more, all kinds of data in a single model, in a single machine learning model. So whatever the data is, whatever the training data is, this is our training data. And if you notice, the training data only goes into our model. This is the whole model. The training data only goes into the whole model through cross attention. And in all places, like this is just take this, block and just repeat it. Cross attention, latent transformer, you get it. So all of this is just repeated. But if you see in all places, we want to get the data through cross attention. So it is a transformer, but the data only enters through the cross attention. So what this can do is this will allow us to make our model deep and apply it on different modalities. Now, by now, you should be able to understand what the term modalities means. It is just can handle all kinds of data, different kinds of data, one single model. And what I also see, let's just see this diagram and follow me along. We'll read stuff later. Um, and what I also see from here, now what you need to do is you need to make observations and try to get your own theory out there, which is a way I like to read machine learning papers and allows me to like also write machine learning papers. Sometimes I'm just reading machine learning papers, making my own theories, making my own assumptions. I try them out, they work well, and I end up writing a paper. My last paper was essentially just this. I was reading a paper. I thought, oh, let's do this. I wrote a paper about it, and it was in one of world's top 10 machine learning journals. So that's also how ideas come to me. And I also, that's why I want to do it this way. So what I see is there is two things, a byte array. A byte array is just this thing, which is our image, or any kind of modality of data, which is our data. Let's just generalize it. Our byte array is our data. Then we, just a moment. Wow. So what we have over here is the byte array and the latent array. So what this also tells to me is M is much larger than the number of latent indices M. So this essentially tells me M is greater than N. And what this is essentially that my latent array is very much smaller than my byte array. So if this is my latent array, which you can see in the diagram, and this is my byte array, latent array is very much smaller than byte array. That's what I see from the diagram or the model or the model diagram. So, and this also tells us that this is our byte array, right? Which is the data. So the data is coming in multiple times. The data is coming in multiple times through a step, and weights can also be shared. So you might think at now that this is an RNN in some ways. Yes, you are right. You are right. This is an RNN in some ways. And what this ends up doing is, in part, it solves the transformer's quadratic memory and compute bottleneck. So if you see, there is nothing modality dependent over here. So what we do in transformers is, so essentially you can apply transformers on an image, right? But you can't apply it on an image directly because you need to do batching, all kinds of stuff on the image first. Here you are doing literally nothing on it. Here you are just taking the image, passing it in. So this could be any kind of data. That gets us to the modality independent part. Could be videos, audios, point clouds, images, all kinds of things. You get the idea without changing the input. So it's kind of really cool applying transformers to very, very different modalities. And yes, this is also a state of the art paper. This is a state of the art paper, which is something really cool. So let's go on to see what this says. These priors, by these priors, it means the existing vision models introduce helpful inductive biases, but also lock models to individual modalities. In this paper, we introduced the perceiver. Now you might also have got the idea of how the name comes up. And okay, so let's take stuff until over here, and let's see what the current vision models do. So what the current vision models do is, so let's say we have an image processing algorithm, which you use currently also. And let's say this is an image. This is our image, okay? And now I have an image processing algorithm. So what our prior image processing algorithms will say is, they'll take this whole image and take this as a grid, which is why I draw this grid. So what our prior image processing algorithms will do is they'll take the image or assume that the image is a grid. They'll think that the image is a grid, and you can take the values of any pixels by their x and y values, is what our current image processing algorithm saying. And the values of the pixels around this, so probably this pixel, this pixel, this pixel, is related to the value of this pixel. So you can understand the value of any pixel by the value of pixels around that pixel. And literally all the current image processing algorithms, all the current algorithms are based on this assumption. Uh, so you can, so if you even take convolutional neural networks, they do the exact same thing. So if you have this image, they'll probably take this, they'll probably understand this pixel as a mix from this pixel, all the neighboring pixels. So that is how convolutional neural networks also work. And well, only after pooling it's done, information across larger distances are incorporated. So what a convolutional neural network says is, let's draw the same image again, that the value of this pixel cannot be affected by this pixel. And only after pooling is done, you can transfer information across larger distances. So, and even if you take a look at VITs or vision transformers, this was all about CNNs and how CNNs work. But even if you take a look at vision transformers, so what vision transformers does is also it uses transformer-like attention. So it uses exactly transformer-like attention, but it can't, right? It can't use transformer-like attention on images because images are really large. So uh, if you just have, let's say, 24 by uh, 24 pixels, this will make it 24 squared pixel values, right? So you can't apply transformers on such large images, on such large sequences. So what a VIT will do is essentially it because it is too much in a transformer, so it will make patches out of this. This is okay, yeah. So this is one patch. This is second patch, third patch, fourth patch, and so on. It will make patches out of this, and it will subdivide our image into patches. It will take each patch and make a vector out of it. So essentially, pixels close together are one vector or a group. And so the paper also says that all current computer vision architectures have this built-in assumption somehow or the other, uh, that each pixel is you can understand each pixel by the values of pixels around it. And every single computer vision architecture up until now has this assumption built into it somehow. And so other modalities have that too. So if you're working with audio data or if you're working with video data, you'll take some of these other assumptions. I showed the assumptions for an image, but for audio data, for video data, all kinds of modalities, you have different assumptions. So the perceiver model, which we were seeing, should go above and beyond that. So let's continue reading the paper. Abstract. Yeah, paper abstract. And so they say that perceiver builds upon transformers and hence makes few relations about architectural assumptions about the relation between its inputs, but that also scales to hundreds of thousands of inputs like coordinates. So let's continue reading and then we'll see. The model leverages an asymmetric attention mechanism to iteratively distill inputs into a tight latent bottleneck. Let's take this part later. But what it essentially says is with a vision transformer, you have with a vision transformer, what you do is you essentially take this 24 by 24 image and make it something smaller. So 24 by 24 image, let's say, so 24 by 24 image, let's say becomes 12 by 12 image, something like that. You make the image smaller. But so and this does not allow it to scale very much. You cannot use vision transformers on very long sequences, as we talked about. So if you see, transformers are simply stacks of self-attention layers, right? So so let's say I show how data works. Let me do this. So what you would want to do with a transformer is, because it is simply a stack of self-attention layers, you want to convert the input to an equal length output sequence. Because I don't know if you know, but transformers were originally for text to text. That is what the original idea of transformers and how it came. So let's say this is my input sequence, 6. I have 6, and this could be actually many. So let's just say these are m numbers. Then I have a stack of attention layers. I have a large number of attention layers over here, and this is also m now, by the way. So I want to convert the input into an equal length output sequence. This is 6, this is also 6, equal input and equal output. This is what a transformer takes as an input, this is what transformer gives as an output. Simple. In the middle, you have the attention mechanism, uh, which computes weights for every one of the inputs and outputs. Now, if you see so with transformers, if you see what is the complexity of the attention mechanism, so we say time complexity, compute complexity, bigger notation. You remember any of that? So if you see the compute and memory requirements for the attention mechanism, those are big O of m squared. M is the number of sequences we have, right? M is our number of sequences. So attention mechanism between these sequences has O of m squared. And if m is small, there is no problem. If your m is small, there is literally no problem. Use attention, you are off to a very, very good start. So that is why transformers work so well in NLP, and they were used in NLP very well. Because in NLP, what you do is you have your M, which is in order of 1000 or 10 cube. So in NLP, you usually have your M as 1000, 2000, 3000, 4000, so on. So it is in the order of 1000 or 10 cube. And for that, using transformers in NLP is super easy. No problems with that. But the problem comes when you use this in computer vision. As I said, in Perceiver, what you want to do is, because I showed you how humans work, Perceiver wants to take all kinds of modality of data. You give it an video, you give it an image, audio. The Perceiver model should be able to work on everything, and it does work on everything. So uh, this is a normal transformer, and in NLP, no problem because M is in the order of 10 cubed and so on. In computer vision, let's say I have an image which is 224 by 224 pixels. 224 by 224 pixels is essentially 50,176. You see where the difference is coming from? This was in 1000, 2000 range, and now this is 50,176. And our compute and time complexity was m squared. And this is unscalable for the computers we currently have. The current computers, our current technology cannot take m such a big m. And that is why normal transformers fail to work on computer vision applications. This is just too huge for our computers. So what this paper asks is they propose a question. Can't we do a better job on this? And that is what we'll be seeing. So before that, let's just see what a transformer does. So you already know equal size inputs to equal size outputs, but let's take another kind of way of showing transformers. What they do, this is our input. On the right side, I have output. Super simple. Both of these are equal size and no problem. So what each of them will have a query, key, and value. Query, key, and value. So what the transformer actually does is it creates queries, keys, and values. These queries, keys, and values get mixed in the attention mechanism, which we have in the middle. And if I take all queries, I'll just write over here. Queries are of the size m cross d. And keys are of the size m cross d too. Keys are of the size m cross d as well. And so when we multiply both of these, so what it does is all of these queries, keys, values get go into the attention mechanism, and then the attention mechanism gives us outputs, query, keys, and values. So queries is of m cross d. It is a matrix, right? So it is m cross d, and when you multiply it with keys, so what you do is you multiply queries with keys, and whichever query and key pair gives you the highest multiplication has the most relation. And that is how you select the query key pair. So when you multiply this with the keys, which is also an m cross d matrix, right? So you'll of course transpose this. So what you'll get is you'll get the final output of matrix size as m squared, right? Simple algebraic maths, you'll get an output size of m squared in terms of matrices. And this is where where we get m squared. and it becomes just too huge for our current computers to handle. So if you remember the very first transformers, the original transformers, they were very much like generative networks. So we have two sequences, the very first transformers, okay, and how the idea of the very first transformers came. If you see that, those were very much like generative networks. And let me show an example. So 1, 2, 3, 4, 5, 6. This is our sequence A. This is our sequence B. This can have more, but we have two sequences, A and B, but the next sequence is incomplete. I only have first two data things. This sequence B is actually incomplete. So there is a clear distinction between sequence A and B, and B would have a self-attention stack. So a stack of self-attention would be on B, and we need output from the last one to know the next element of it. So you need the output from a self-attention unit below it to know the output of the self-attention mechanism above it, and so on. However, the input did not use self-attention. Our input did not use self-attention, but use cross-attention. So, uh, from here I'll get my keys and values. Here I'll have my queries, and then I have multiple stacks of self-attention, so on. And then query from here goes away, which will place, which will place, right? So we'll take the outputs from the self-attention. Sorry for that. So we'll just take the outputs from the self-attention and use them to uh, fill out B. And now you should notice that our sequence B should not be the same length as sequence A. That's not a necessary thing. And because the queries are generated from sequence B. So if you see our queries on QKV, so remember QKV were generated from the input, and now we have a sequence B. My queries are generated from sequence B. So sequence A and B do not need to have equal length. Because my queries are no longer generated from A, they are generated only from B. So instead of the M cross M matrix size, we got the output as M cross M matrix. Instead of that, we can now have M cross N matrix, where N is a number which is smaller than M. So from M cross M matrix, I go to M cross N matrix, where N is a smaller number. And if our N is quite smaller than M, well, what would happen? So remember this part I talked about, O of M squared, which introduces a quadratic bottleneck. And we call this call the O of M squared as quadratic bottleneck. So quadratic bottleneck, because you know why, right? To the power 2 and so on. So if you make this from M squared to M cross N, and our N is very, very smaller than M, there is no quadratic bottleneck. The quadratic bottleneck you saw runs away because it's no longer an M cross M matrix, but an M cross N matrix, where N is very much smaller than M. And that is exactly what this model will do. And that is exactly what this model will do. Let's go back to the architecture, see some more over there. I think that will make it better understandable. Let's erase these annotations. And if you see, our goal is to have a latent array. So we'll use the same M and N notation. Queries, keys, values, same notation, same notation. So you will not get confused at all. So our goal, I want my M to be very much greater than N, right? That's my goal. So if you see, where do I see N in this architecture? Oh yeah, that's right, in the latent array. So I want my latent array to be as small as possible. Latent array should be very small. And n should be a size that you can handle in a regular transformer. So when I say you can handle in a regular transformer, I mean something like 1000, 2000, and in the range of thousands that you can easily handle in a regular transformer, right? So if you see the top row, all of this, let's just circle it once. This is just uh, this is just regular self-attention transformer. Nothing new in the top row over here. Regular self-attention transformer with all the drawbacks we talked about. But because we only have sequences of length n, the classical self-attention modules, or the classical self-attention modules which we have, let me do this. Yeah. So all the classical self-attention modules which we have, and this goes on, right? There's these three dots. So all the classical self-attention modules will now have no problem because n is relatively small and we can handle it in current hardware. Uh, the problem comes when you bring in images. So in this paper, they take an image and unroll it into a byte array. So you want to take every single image, which is 256 by 256 and so on, and unroll it in this byte array. Uh, and so still note that M is huge, like the 50,000 scale we talked about. But see a really cool thing. Now, stay with me on this. Our byte array is really huge. This is probably 50K of the, the range of 50K and so on. That is how huge our byte array is because this is an image, right? You do a 256 into 256, you get 51,076. I did the calculation earlier. You get that. So this is very huge. But notice one thing. What does the image produce? Let's follow this arrow. Oh, yes, it only produces keys and values. Okay, where are the queries produced from then? Or in earlier transformer, you will have something like queries also from here. Simple. This you just directly generate QKV from the image. This layer does not do that because my let's see where my queries are generated from. My queries are generated from latent array, and latent array, as we talked over here, is very small. So because my queries are generated not from the image, but from the latent array, which is very small, there is no bottleneck. So the latent array is m n by d array, and byte array is m cross c array. So there is so there is no longer the quadratic bottleneck we saw, and it can also handle all kinds of sequences. So when the image comes into the transformer, this is our image, right? So when the image comes into the transformer over here, what we see is from the cross attention module, and it is not converted into an equally long sequence. It would be converted into an equally long sequence if my queries were also generated from the image. But because my queries are generated from the latent array, it comes into the attention module and is not converted into an equally long sequence, but a shorter sequence. So from that, now we have a transformer transforming into a new latent state from the queries that are generated. This is our new latent state. After this, I again have the latent transformer generating the new latent state. And now the queries are generated from this new latent state, which is smaller than an image. Uh, so we'll call this generated thing latent state. My image is now, or everything in the image goes into this short latent state, which is a very short sequence. So interesting mention in this paper is this reminds us of RNNs because there is one thing which you probably didn't see or you might have seen. This says weights optionally shared between repeats. And if you didn't see it until now, this does remind us of RNNs. But if you see, especially if you want to share weights between repeats, this looks very much like a standard RNN. And uh, because weights can also be shared between repeats. And yes, in some ways you can say it is similar to how RNNs work. Um, so the latent array at the start could be randomly initialized, or you could also learn it. And so this is pretty similar to RNNs. And in fact, is an RNN a modified RNN if you share weights? If you share weights, you essentially say you want to learn queries as opposed to generating queries. You want to now learn your queries. And if you do some switch up over here and pass different data batches in each inputs, so this is a different data. Yeah. This which you see is a different data batch. This you see is a different data batch. Earlier we talked about all of this were the same data, but if you make minor touch-ups in this, minor modifications, I also tried doing it in code. I'll show you some of it after the talk, but I also tried experimenting with this, forming my own kind of addition to Perceiver. But if you do some switch up over here and pass different data batches in each input, you will truly think of RNNs. This is truly an RNN. And that's also how I kind of got the idea to do that. I had RNNs in mind and just had to do this. So in a way, you can think, you can also think that uh, you generate in the latent array is a generic set of queries. So okay, let's see it this way. So what I generate in the latent array, let's go down. Yeah. So what I'll be generating in my latent array. Now you remember what latent array is, right? So what I'll be generating in my latent array is is a, is a generic set of queries describing what you want to know about the image. So what essentially queries do is we have three terms, right? Queries, keys, and values. So queries tell us what I want to know about the image. I'm just taking the example of image over here because I have a tilt to computer vision, but you can do this with any kind of data. I'm just saying image to put things into perspective, probably give you some imagination too. So I can you'll generate a random and very generic set of things. These are all things you want to learn from the image, or you are saying this is what I want from the image. These are the features of the image which I want. So all of these are vectors. This is probably this vector, this vector, this vector. Yeah, all of these are different vectors, and you could say, and this will be very small. Queries will be very small. Let's say you have 1,000 of these, and then you have 50,000 keys, which is the standard. We talked about standard computer vision scale. And these are also vectors. These are also vectors. And what you want to do is, out of these 50,000, again, these are just representative numbers. Out of these 50,000 keys, which is what you can learn from the image, you want to choose only 1,000 queries, which is what I do want to learn from the image. I want to choose 1,000 criteria to gather from the input data. And keys like, say, for every pixel in the data, what kind of information the pixel offers. That is a key. What kind of information every single pixel in the data has. So that is of the size 50,000. So you have queries and keys more than queries. So each of these exposes a vector, and out of this you route the information or points which have a higher inner product. So you'll find the thing, find the points which have a higher inner product. So you may be accustomed to different terminology. So like in my school, we only use the term dot product. So for those people, inner product is just a generalization of the dot product, and not to be confused with the inner product space or T2 space if you have studied it that way. So every key will now have a vector associated with it. And if you do it, once you get the generic information, you get the quite generic information, but the later queries are a result of the pre-processing. So if I see again to the architecture, this query, which is a later query, right? It's not the first query. That is a result of the pre-processing from this query. So you are essentially refining and refining for more specific information. First, you wanted very generic information. Now we are going for more specific and more specific information. So you're learning more and more about the data dynamically, asking it what you want to learn from it. I think this is pretty good and solves quadratic bottleneck as well, which is really cool. Now, this isn't just something to solve the transformers quadratic bottleneck, but also allows building deeper transformers. You can build more deeper transformers than ever. And uh, and the paper authors also present that the best results for ImageNet were actually seen with 48 latent transformer blocks. And if you do it with weight sharing, the number of parameters are comparable to a standard ResNet model. So pretty cool. And it might be possible to train a network with 48 transformer layers for some NLP problems, but that's quite some amount of hardware. And with this perceiver architecture, you can train a 48 layer transformer very easily, which is really very cool, I think. And if you see the next page, you also see they apply it on point clouds, they apply it on videos, they apply it on audio data, all kinds of data. So this is also modality independent. So yes, they don't put all the videos at once, but they put in chunks of the video. So you can, in some way, say still doesn't solve to say all problems. You can't have a data point as huge as a whole video, that, but works pretty good for all other modalities. And well, because things are now linearly huge, we just solved the problem of it being quadratically huge, which is, I think, pretty cool. So one last point we'll be discussing about the architecture is let's again go back to the architecture. And so let me just remove all these annotations again. Let's keep this. Okay, so input is essentially independent. It could be image, it could be audio, truly modality independent. There is no stuff like filters in a CNN architecture which only work on an image. If you give a CNN some other kind of data, you'll have to make drastic changes in the architecture. No such thing over here. Works on all kinds of data. There is nothing like patching, batching, all of those stuff we do in ResNets, VITs, which only work for images, make heavy assumptions that the data is an image. Nothing required over there. So the thing is, transformer takes no account of the order. So, but in things like text, the word order does matter a lot. So if you are working, let's say, with a transformer will probably think 1, 2, 3, 4, and 4. I don't know what happened. Okay, 4 to now it's working well, and the S Pen hanged for a bit. So a transformer will probably think both of these are same. And but for things like working with text, the word order matters a lot. So you want to have the model exploit somehow, but not build it into the architecture, right? We want modality independence. So I want to model to somehow uh, exploit the position of the data. So let's just go to the section where they also talk about how they can take into account positions. Oh, just if you wanted to see, there are also some metrics which we'll soon see. So if you go to this section 3.2, position encodings, and I'll not want you to read all of it, very huge, math heavy, no problem. So we give positional encodings. So the way positional encodings is done in this paper is Fourier features, much like the previous transformer papers where you had Fourier features. Uh, so, uh, so what you do is you have multiple, let's say, you have multiple waves. This is one wave. This is second wave. You see what's the difference between these waves, right? This is the third wave. These are all our position encodings, which represent where which position our data is. So at some point, you'll find common ground for all of these. I know this is not the best drawing, but at some point, you'll find a place where all three of these coincide. And that is how you'll also take into account the position. Now, you may think that this may not make this model non-domain specific. You don't rely on the fact you have a maximum amount of sequence length, and you are essentially telling it's one less thing to learn. Learning happens in the processing, right? And Fourier features are naturally quite trivial to adapt to new modalities. They can also be extended to multimodal data. Each domain uses a position encodings with the correct dimensionality, which the paper does for one of their experiments on the ODE dataset, where it achieves SOTA results. It is essentially the best architecture for that kind of problems. So yeah, so for each kind of so let's say if you're passing in images, you'll have the number of dimensions set to be 2. If you pass in videos, you'll have the number of dimensions set to be 3, and so on. So that is how it still handles not being domain independent, but also allows you to take in positions into the model. And I think that's pretty cool. Let's come to the last part. Let's see this table, which is actually quite interesting to see what just happened. I don't know, something happened, and I just got. Okay, let's see this table, which just shows how well this model performs. And if you see, the perceiver model is actually doing pretty well on images and top one accuracy of the perceiver model. This is the top one accuracy, you can see. Essentially same thing as saying accuracy, nothing new over there. But the top one accuracy of perceiver is comparable to a VIT, to a ResNet 50, and yeah, it's actually comparable to a ResNet 50 and VIT, which is, and yes, this is without the assumption that the data passed is an image. So while training ResNet 50 and VITB, they achieve 73.5% accuracy, 76.7% accuracy on ImageNet, but both of these architectures were fed in the assumption. So they had taken an assumption that the data passed in is an image, whereas our perceiver model, it gets an top one accuracy on ImageNet of about 78%, which is quite comparable to these, better than these actually. But it also did not take the assumption that what it gets is an image. The model did not know that what it will be getting is an image. So that I think is really cool. And I think you'll think it is cool too. So except the Fourier features in 2 dimensions, nothing at all in the model says that the data is an image. It's just an array of pixel values that the model can handle so well, which is pretty cool. They also show in a couple of really cool visualizations, which I'm sure you'll love to see how well the model performs. So let's hang on. I'll just scroll. They have a good thing over here. Ah, this is a really great image where a lot of this might not be visible to the human eye. It's actually hard to see. Um, So what it shows is these are attention maps of cross attention layers of model on ImageNet. So this has 8 cross attention layers, and layers are 2 to 8. So this also shows, yeah. So layers 2 to 8, this is 2 to 8. This is the second layer. This is the eighth layer. This is the first layer. This is the input image, right? So the layers 2 to number 8 share their weights. And so the layers 2 to number 8 share their weights. And so if you see, these attention maps are not actually put on top of the original image. So this attention map, if you see all of these are not put on top of the original image. These are generated all by the model itself, which is pretty cool. Um, and the slide image structure we see is the attention map itself. So let's just see layer 1. Layer 2 and 8 get too jaggy for us to see. But if I just zoom in on layer 1, you can see this is layer 1 and the attention maps generated for it. What just happened? Oh man, I think it did something. I'll not zoom in too much. Probably, yeah. So if you can see a little bit, that it starts to understand that this is the image of a dog and the surroundings around it. And it is able to identify it pretty accurately, does a pretty great job. And these are the attention maps from layer number 1. Layer number 2 to 8 also have those attention maps. And the layer number 2nd to 7th layer, they look like a grid, heavily rely on positional embeddings. So we probably can't make out exact from it. But in layer number 1, we could visually see the great work attention maps are did. And this performs really well on audio, video, and point clouds too. So yeah, that was pretty much about the presentation, about the paper we were about to discuss. I'll share my screen once again. And this time what I'll do is I'll share my full screen. So yeah, you can see my screen now. And so yeah, that was all about the paper. And I hope you had fun discussing the paper. I hope you learned something new from discussing this paper. And feel free to try out feel free to try out more from this paper. I would encourage you to try out more. If you have any questions, feel free to ask them to me right now. I also have a code implementation of this paper. I made a code implementation of this paper. So I also have the code implementation, which you can try out. And there is also a collab notebook for you. If you just go in examples, pursue your example. So this is a collab notebook. You click on the open in collab button over here, and you can run everything in the browser itself. And if you want to try it, I've also made this as a Python library. So you can start using this in your projects, which I think is pretty cool. And feel free to, so this is essentially this code repository is exactly what we talked about today. We talked about Fourier encodings. We talked about self-attention mechanisms. All of that. It's exactly what the ideas we talked about. I converted them into code and put them over here in this repository. So I'll just put the repository link in the chat if anyone wants to see. And yeah, feel free to check this out to probably start using it in your projects if you want to. So that was all about this talk from me. And and if you have any more questions, I think now is the time. And if you have any questions in the future as well, feel free to connect with me on any social media. Ask me any question. I'd be more than happy to help you out.